Good morning, everyone. Good. 8 o'clock is not the best time for kicking it off, is it? But I teach all my classes, and I got some of my students here, and you know, I always teach an 8 o'clock class, and when they evaluate me, the class at the end of the semester, the one complaint is, don't teach an 8 o'clock class. I always get, but you know, a lot of them want to be golf course superintendents. And so I tell them, you know, you're welcome for letting you sleep in because you would have already had 3 hours of work in by 8 o'clock if you're on the golf course. So it's a good way for me, a good litmus test for me to see what students can get to an 8 o'clock class. So when it comes to them applying for jobs and me giving references, I know which ones can be there for an 8 o'clock class, and I know which ones I can say, hey, this would be a good one to go on the golf course. So, but like Jason said, I'm John Sorochan at the University of Tennessee. Been there 18 years now, almost 18 years. And I love giving this talk because turfgrass and shade is what got me into doing turfgrass research. Because I went to Michigan State, I wanted to be a golf course architect. I went through their 2-year turf program. And while I was there, I was going to say, I'm going to finish my degree because I transferred from the University of Calgary. And that happened to be when the World Cup soccer was in the U.S. in 1994. And the biggest challenge was for us for the World Cup was Detroit was a venue, and they had to figure out a way to put grass in the Pontiac Silverdome in Detroit for 4 World Cup soccer games. It had never been done before. And so, you know, I was an undergrad at that time, and I worked for Trey Rogers, who was the professor overseeing that, and John Steyer, who was his technician. And that's where I got exposed to doing research, sports turf research, and shade or low light research. So the World Cup, and we had to figure out how to keep it alive. We grew it in modules in the parking lot, moved the field in. It was a big success. So after that, I realized I wanted to do sports turf work, and you know, my PhD was looking at managing turf under low light conditions as well. But when it comes to managing turf, grass, and shade, you know, the first and primary thing to think about is light. There's the absence of light, the lack of light. And what happens as a result of that? You know, the simple definition of photosynthesis, plants take sunlight, absorb CO2 through the stomates of the leaves, take up water through the roots, and they convert it to carbohydrates or simple sugars. And that's the energy that's going. A lot of you guys have coffee with caffeine in it. Some of you got Mountain Dew with a lot of sugar in it, so you could stay awake, get that energy to listen to me talk, right? So I don't put you to sleep. You need some boost. You know, plants get theirs from the sun. They get their in CO2 and water. And that's the backbone for the way plants grow. Now, if you inhibit any of this, i.e. block out the sunlight, you're going to affect how that plant can produce its own food or energy. The light that's used, you know, 2% of all the sunlight that hits the earth is only 2%, 1 to 2% of all the sunlight that hits the earth is actually used for photosynthesis. And that's the visible light spectrum. We call it photosynthetically active radiation. And basically it's the colors that make up the rainbow from about 380 to 700 nanometers. So the wavelengths that we can see as visible light is what plants use for photosynthesis. 2 components of light are light quality and light quantity. And light quality are the individual wavelengths, so the measurements of those 380 to 700 nanometers. And you can wave them down, and you go very short ones would be down here, cosmic or X-rays. You got ultraviolet light. Really long waves are radio waves. But in that visible light spectrum of 380 to 700 is what we call photosynthetically active radiation for plants to grow. Light quantity is how much of each of those individual wavelengths is there. So it's the energy, and this is what's most important for photosynthesis, is how much of that light is available for the plant. The shorter the wavelength, the more the energy. So if you got that visible light spectrum, the violet and blue light, right around here, those wavelengths are shorter versus the red light, which is a longer wavelength, so it's less energy. A good analogy is to take this tablecloth. And if I was to take this tablecloth and start waving it, the distance between those ripples, we could say are what we call nanometers. That's the distance between each wave. I shake it really fast, those wavelengths tighten up, right? Those ripples get closer together. It's more energy. at the same time, right? So that violet and blue light is high energy compared to the red light, which is a little bit lower energy. Plants absorb all the light, all the visible light spectrum, but not as much as the green. That's what's reflected back. That's what gives the grass its green color to our eyes, right? And as we look at it, violet light, less than 380, ultraviolet light, plants use that, but they mutate cells. Just like ultraviolet light mutates our skin and can cause us to tan, or if you're a ginger in this room, you can burn, go red, right? Or it could even cause mutations and cause cancerous skin cells. So we try to protect ourselves from the ultraviolet light. Well, historically, everyone's heard of Tifway 419, Bermudagrass, right? Dr. Glenn Burton released that. Well, when Dr. Burton used to do breeding back in the 50s, he would go from Georgia up to Oak Ridge National Laboratory just outside of Knoxville, Tennessee, where I live and teach. And he would bring up bunch of sprigs of Bermudagrass and take them to the laboratory, because back then they didn't have the availability of all the technologies around the world. And he would expose sprigs of Bermudagrass to high-intensity ultraviolet light. And what it would do is it'd cause mutations in that plant, and that plant would then cause genes to be expressed. And then he'd go plant them in the field and see what happened. And sometimes it didn't do anything. Sometimes it created a weird-looking Bermudagrass plant that was useless. Maybe it grew more, so it became a forage grass. Sometimes it had a dwarfism gene that was expressed, and they come up with dwarf types. So they could release different types of grasses. So it was a tool used by breeders back in the day to help develop new grasses. But the visible light spectrum, again, that violet and blue light, when the plants absorb that, it's a stimulus for that plant to have short, sturdy growth. The green light, as I said, is reflected back, gives it its color. Red and yellow light absorbance causes that plant to elongate and stretch out. And so there's two different stimuli from the visible light spectrum that the plants receive. Seed germination is what we get from far red light. Actually, looking at managing turf under low light or plants, we're learning that the inclusion of some far red light helps. And this is coming more so from the horticulture industry, and I'll talk about that near the end when I get into some of these lighting structures, looking at high-pressure sodium versus LED lights. We measure light in terms of energy, and we look at it as micromoles per meter squared per second. If you're close to the equator and it's a really sunny day, no humidity, no clouds, you might have 2,000 micromoles per meter squared per second. Where I grew up in Calgary, Canada, on the sunniest day, because it's so far north, you might get on the sunniest day 1,500 micromoles per meter squared per second. But you do have like a 20-hour photo period almost, but at the same time, it's not at the highest intensity, it's not very intense. But we measure it in what we call micromoles per meter squared per second. And we measure it with a device called a spectroradiometer. Now we can add a photospectroradiometer, and we can measure what the individual wavelengths are, the intensity of the blue light versus the red light. So you can measure different ways. But, all of that is meaningless without a time factor, because at that one instance is just a snapshot in time. But what we want to do is how much light does that plant get throughout the day, so we can look at the total irradiance dose, or the DLI, if you want to call it, daily light interval. And a full sun day under ideal conditions could be about 60 moles of light per day. But we get variations in how that light quantity is received. The season, depending on how far you are from the equator, but the summers, longer days, more intense light. Again, where I grew up, sun comes up, 4 o'clock, 4:30 in the morning, it's light, doesn't get dark. You could go tee off, play 18 holes of golf at 6 o'clock, sit down, have a couple jugs of beer. It's 10:30, 11, and it's still light, right? Wintertime doesn't get light till 9 o'clock in the morning, and it's dark by 3:30, 4 o'clock. So the latitude and the seasons have an effect on how long your daily light intervals will be. Atmospheric screening, high humidity. We're in South Florida right now, and it's 80 degrees out, lows of 70. It's optimal temperatures still for Bermudagrass to grow, yet they still have some shade stress because the days aren't as long, time of year. Afternoon clouds roll in, you get screening, light's reduced. The humidity in the air helps dampen the effect of the light coming to the hidden thing. You know, air pollution, dust, all of these things can affect, you know, the intensity of the light. Topography, well, this isn't much of a problem in sports turf areas, but, you know, on golf or things, you have a north-facing slope. That's going to cause shade. Instead, you get it from jumbotrons or overhangs on the stadiums that cause shade problems in stadiums, right? So shade, you know, is an issue. Some of the effects of low light quantity, you get that reduced photosynthesis. With reduced photosynthesis, you have lower energy levels, poor recovery from damage, poor density, and your plants are less stress tolerant, poor stress tolerance. So they're more susceptible to diseases or insects. So there's a lot of problems that can occur. We can measure light variances throughout the day, and this is an example of measuring over a 24-hour period. This happens to be Madison, Wisconsin, and you measure how many moles of light per day are happening. 6 in the morning, 7, 8, 9. Starts to get bright, highest part of the sky, at the solar zenith, the apex. Sun's at its most intense between 12, 1 o'clock. Starts to come down. It's not a perfect bell curve because there's a little blip. A little cloud moved in and caused that light quantity to be reduced. Normally it would be over here more. So you can see how there's variances. Seasonally, there's variances too. So this is the same, Madison, Wisconsin. The sunniest day, they had 44 moles of light in that day. Again, it's further north. They can't get to that, achieve that 60 moles of light per day. But cool season grasses are more shade tolerant than warm season grasses because they're more adapted to lower light. That's where they've evolved. But you can see, even in the midst of summer, cloudy, rainy day all day long, you know, you've had shade stress applied to your turf because it's only had maybe 15, 14 moles of light that have applied. Doesn't matter in January and February or November how much light you're getting in Wisconsin because the ground's probably frozen in 2 feet of snow, right? So not as big of a deal, but it does matter for the Green Bay Packers, right? Because they had a playoff game. This is the light intensity in January. Not a lot for that bluegrass to grow, so they have supplemental light to grow the turf in Lambeau Field. So plants absorb sunlight. Here's the wavelengths of light again. So the violet and blue light to the red light being absorbed. When you add shade, it changes that ratio, and it changes the quantity of how much light's being absorbed. And that's where when you get that turf in the shade, you get that elongated, etiolated leaf stretching out because of the lack of sunlight and that change in red and blue light ratios. So, you know, the ideal light hitting, whether it's a tree or a stadium overhang, that's dampening the effect, the quantity of light coming through. And you think of these stadiums that they build and they got the big overhang. The light's coming down. It's blocking it from directly hitting the turf on that southeast corner, let's say. So the light has to bend around. And that ambient light that bends around now takes those wavelengths and stretches them out and loses the energy. It loses that energy, and you get that red light stimuli of that elongated. You lose that short, sturdy growth that you get from blue light. So full sun versus shade, you get just these variances, portion of each wavelength. Different trees cause different shade. Buildings cause more of a shade because some of the light transmits through different trees to get down to the turf. It's not going to transmit through a building, so it's got to bend around. So it's going to really reduce and dampen some of that energy. What happens? Light quality, you get delicate leaves that damage easy. High succulence leads to disruption under traffic. Sorry, we got a stadium that's got a big overhang and it's heavy shade, so we can't play on it because the turf's under too much stress. So you're going to get damage from it. You can't do that, right? You can't cancel games because of that. So these are challenges. So the low red light, this should be causes rapid growth. You get that reduction from the blue light. But where do we see shade stress problems? Where do we find shade? this is a picture of Hamburger Land and Golf Club in Hittfeld, Germany. And, Michael Paletta is the general manager. Frank Schaefer is the superintendent. Two good friends of mine. One of the single most shady golf holes I've ever been on. This is their number 16 tee, coming to par 3, coming up towards the clubhouse. And it's just heavily shaded on all sides. So we see it on golf courses. This is their number 1 green. Lots of problems, lots of shade stress. Trying to cut down a tree in Germany is like an act of Congress. They love their trees. They love to hug their trees in Germany, apparently. So they were able to take some of these trees out, raise this green up 5 meters, and it's still under heavy shade. But you can see how shaded it is. Home lawns, we see a lot of shade. And stadiums. This is Amsterdam Arena back in the late 90s. And, heavy shade, retractable roof or covered roof. And what they did at this point, back in the 90s when they built this stadium, was they resodded that field 4, maybe 5 times a year. They put the sod in. They were buying bluegrass sod from England, so it wasn't cheap, shipping it up, sodding it. And as soon as they put the sod in, they were constantly throwing ryegrass down. That's why you see all the pigeons out in the middle of the field. They're eating all the ryegrass. Russ, you would love it because you could sell a lot of seed to these stadiums because they're just trucking the ryegrass, but because there's so low light. So what they would do is they would schedule a concert. Apparently the Dutch love like Madonna and things like that, so they'd schedule a Madonna concert and charge an extra €7 for a ticket. And that €7 paid for that sod replacement. Well, the club got tired of this resodding. It was very expensive. So they wanted to solve this problem, so they went to a gentleman named Nico who grows roses in the Netherlands, and some of the highest quality red roses in the world that you can buy. And he's got these high tunnel greenhouses with high-pressure sodium lights in there, and they're like, can you help us? So that was what spawned SGL, or Stadium Grow Lights, to come in, and they've put grow lights in the stadium. They don't resod it anymore because they got the grow light technology to help sustain photosynthesis, because that's supplementing the sunlight that was missing. This is what it would look like when they put the sod in. You don't have enough sunlight, enough photosynthesis to produce energy, so what that plant's going to do is it's going to put all its energy that it does have into new shoot growth. It's going to lose its density, and it's not going to produce roots. So that sod would never set roots if it didn't have additional lighting in there today. So it looks good from a distance. You stand over it. It didn't. It didn't play well. Other stadiums, they like to put the jumbotrons on the south end of the stadium in the northern hemisphere, because that way the sun doesn't hit the screen and you can actually see it. That's the way it adds a nice block of shade as well. So you can have stadiums with jumbotrons or different things that they can to block it. Skyboxes, overhangs, all these things can cause shade stress in stadiums that you don't normally think about. Not the highest quality resolution image, but the UK, they sure love, it's always raining, so they have to keep the spectators in comfort. So there's overhangs over all the spectators. Causes a lot of shade, plus they're 53, 54 degrees north latitude. There's seasons going on now. Days are short. So heavy shade stress issues. And if you go back and you look at all the old footage of games back in the 90s being played of soccer, the EPL pitches, they looked like crap, right? They didn't look very good. Today you watch it, the fields are all the pitches are perfect. They're flawless. And, a couple of technologies have come on. They've got sand-based root zones, and I think every EPL team has some sort of stitched hybrid system in there to help stabilize the sand for the ryegrass that they're growing. And they all have grow lights. Is there one EPL team that doesn't have a grow light? Every single stadium has a grow light, right? Some of them have more than others. Some of them have it just for that south end, and they move them on the other end. But some of them have for goal boxes. But, you go to Tottenham, and they got it. They can cover the entire pitch with grow lights and grow. So at one time. So overhangs, even outdoor stadiums in the fall. How many of you are from the Pacific Northwest? So Russ, up in Oregon, Seattle, cloudy, rainy, drizzly. Temperatures are still good for cool season grasses potentially to be growing along the coastal areas, but the low light days cause for a lot of stress even on a stadium that you wouldn't think has shade problems. Similar to an ultra-dwarf Bermudagrass putting green here in South Florida. You're mowing it really short, and high humidity, short days, cloud cover all the time. These greens get some shade stress. The Gelderdoom in Arnhem, Holland, was the first stadium to come up with the pitch that would move in and out of the stadium. They can have all the events they want. This is a good way to solve that problem. Now we see multiple stadiums. Next year, the Raiders in Vegas are going to have a stadium that does that. This is the way to go if you can do it, right? Move it in, do whatever you want, move it out, have concerts, trade shows, whatever you can do to host events. Arizona Cardinals Stadium, they did the same thing. Field moves in and out. Talking with Trey Rogers, who was working with the architects in it. If you get the chance to work on a stadium build, make sure you talk to the architects first. A lot of problems come from architects. They want the feng shui and they want the stadium to look great. The last thing they think about is the quality of what they're going to provide for the pitch, right? So if you looked at the original architectural design for the Arizona Cardinals Stadium, it was great. The field comes out from the stadium. You can do whatever you want inside. Problem was they had it coming out on the north end of the stadium, right into the shadow of the stadium. Trey said, turn it 180 degrees. The architect didn't think of that. Turn it 180 degrees so when you take it out of the stadium, it's in the sun, right? So don't trust an architect. If you get one thing from here, don't trust the architect. We've had indoor turf. 1965, there's Bermudagrass in the Astrodome. Where they played one season on natural grass in the Astrodome. Outfielders complained that when there's pop flies, the glare off the glass from the sun, they couldn't see the pop flies. So their solution, paint it black. Paint the glass black. Killed all the Bermudagrass. I don't know, it's my conspiracy theory that they knew that was going to happen. They wouldn't let them put artificial turf in. At the time it was called chemgrass, developed by Monsanto. And the reason that artificial turf was originally developed was during the Korean and the Vietnam War, when there's the draft going on, they noticed that inner city kids were less fit than suburbia and rural kids. And they didn't have places to play. So they developed chemgrass, and they started putting it in these inner city parks so kids could recreate and play and get fit. Well, that same chemgrass went into the Astrodome. What did they call it? AstroTurf. And that was chemgrass became AstroTurf. So it was the very first one to go into that. So that's where that kind of little history on that. So shade effects on turf grass. Morphologically, when we look at what happens, you get leaf thickness decreases, plant height and elongation. It gets that elongated leaf. The density decreases. You get less shoots per plant. The tillering, less plants coming off of there. The growth habit, if it's a Bermudagrass that grows by rhizomes and or stolons, or a bluegrass that grows by rhizomes, you're going to get a reduction in that. There's not enough energy to send out that daughter plant to keep growing. It's just trying to survive. And your root to shoot ratio changes as well. Physiologically, you get lower carbohydrate reserves, reduced transpiration of the plant. You can't burn, you can't breathe, can't survive as well. Can exceed photosynthesis when it does respire because it's not producing enough energy. Becomes more succulent, a reduced cuticle thickness on the leaf, so its hardiness. It becomes more susceptible to, if you have a herbicide or a PGR, it becomes more sensitive to things like that. And environmental conditions around shade. You know, doesn't matter what's causing the shade. You know, in the shade, your temperatures are a little bit more buffered, but your humidity tends to be a little higher. Your air movement's restricted. So all of these things can cause stresses on your turf, secondary, tertiary stresses that you don't think about. Again, you get delicate leaves that damage easily. What do? Restrict traffic? Reduce traffic? Can you do that? It's like you can't move your goalposts in your stadium either, can you? You know, it's nice for golf courses. A golf course has a shady green, and it's on that back corner. They just don't put the pin on that back corner as often. They keep it on the other parts of the green, so they just reduce the amount of people that walk on it. You can't do that on your stadium. But you want to closely monitor diseases. You know, watch your nitrogen fertility. I'm going to go into more details on these. Watch your irrigation. It's still simple turfgrass management, managing turf and shade. We have our 5 primary cultural practices: mowing, fertilization, irrigation, cultivation, and pest management, managing diseases, weeds, insects, and athletes, right? So those are the pests that you try to manage. But again, you look at that rapid growth that occurs under shade and low light. What do you do for that? Here's Bermudagrass in full sun. Here's Bermudagrass in shade. It gets stemmy, stocky, almost grows up like a tree that stands up, reduced light. So you can see the restriction. Under ideal conditions, full sun, you got stolon or rhizome growth, you got shoot growth, you got root growth all happening. You put that same turf in shade, everything gets reduced, and the ratio of shoot growth is greater. Still not as great as it would be in full sun, but compared to the root and stolon growth, it's more. So your plant isn't how it's meant to be or isn't natural, so that's where it becomes stressed and susceptible to the environment caused by shade. So how do we manage turfgrass and shade? If it's golf, they move the cups often and utilize the entire green, restrict cart traffic on fairways. You can do that on the golf side, but can you do that on the turf, on your sports fields? No. In your stadiums? No. So monitor diseases, preventative fungicide programs, limit nitrogen, and I'll go into details of each of these. Minimal irrigation. They're not photosynthesizing as much. They don't have as much root capacity. They're not going to take up as much water. You don't need to put down as much water. You don't have to worry about tree pruning, but plant growth regulators are really good at helping, and I'll talk about that. But again, the primary cultural practices: fertilization, irrigation, mowing. Mow at the highest height you can for that grass that's tolerable for the sport you're playing on it. The higher you get that grass cut, the more surface area, more leaf area you can have for that plant to absorb sunlight. Under full sun, you get a nice prostrate growth, high density, green speeds. If it's a ball roll, baseball, it's going to be faster. In shade, poor density, upright growth, things are even faster. A lot of what we've learned is from the golf industry. But looking at shade trials, shade research, picking the right grass. The single most shade-tolerant grass we've got are fine fescue and supina bluegrass. Now, you wouldn't want fine fescue on a sports field, but I've seen some supina bluegrass fields in Germany, and there's some in Scandinavian countries. Great grass, excellent grass, extreme cold tolerance, native to the Alps, does well under low light conditions. The Poa pratensis, Kentucky bluegrass, perennial ryegrass, two grasses, cool season grasses that we typically use for sports turf are the least shade tolerant that we have. And it can be varietal dependent. Warm season grasses, my students know, what place will Bermudagrass come in a 3-horse race for shade tolerance? 4th, right? The single least shade tolerant grass we've got. They'll come in 4th in a 3-horse race when it comes to shade tolerance. So challenges. If you look at comparing Poa supina, which is supina bluegrass, to Kentucky bluegrass, we can measure how plants photosynthesize and we can measure it using micromoles per meter squared per second, similar to how we measure the light intensity. And you put these little growth chambers in, you have the air flowing through, and you measure the CO2 coming in and the CO2 coming out, you know, the surface area of the leaf and all that, and you can come up with a calculation of the reduction of CO2 coming out means that plant's absorbing that CO2 and it's photosynthesizing. Under heavy shade, 3.5 moles of light, extremely low shade. Kentucky bluegrass photosynthesizes at 1 micromole per meter squared per second. Supina bluegrass photosynthesizes at 1.5 micromoles per meter squared per second. Just genetically, that plant is more adapted to low light and has a better efficiency for photosynthesizing under the same conditions. Again, looking at the annual wavelengths, cool season grasses, you know, between 18 and 35 moles of light per day. Well, you could consider, that's for warm season grasses, would be the limits, depending on it. Is it Bermudagrass to zoysia grasses? Zoysia grasses are down on the lower end. The Matrella types have a better shade tolerance than the Bermudagrasses, hence why they come from Southeast Asia, where it's more humid climates. They're native to those areas and cloudy, versus the Bermudagrasses that come from Africa. More sun, lower humidity climates. So that's where those grasses evolved from, why you see those different ranges in shade tolerance of those species. Cool season grasses, you know, you can get down to 9, 10 moles of light per day to 15. That's considered shade stress areas, but they will survive. Warm season grasses won't survive very long in those low light conditions. But again, management. I said already, mow at the highest height you can for your sport that you've got, that you can get away with when you're under shade stress conditions. Limit the amount of traffic if possible. If they're going out and training and practicing in the stadium, you got a shaded stadium, and it's that south end, maybe have them do as much of the training on the other end of the stadium as possible. So communicate with the coaches. Again, looking at this is creeping bent grass, but as you increase the mowing height, now increasing it from 1/8 of an inch to 5/32, or 3.2 to 4 millimeters. So we're talking 0.8 millimeters only on bent grass. It increased the capacity of that plant to photosynthesize by 25%. It could get just that 0.8 millimeters, it could get 25% more carbohydrates. Anything you can do to raise that mowing height is going to help. They get crazy in the golf world now, going down to 1/10 of an inch, 2.5 millimeters, right? Going up to 5/32, it's a 50% increase. You're doubling how much energy you can have in that plant. So think of it, if you have your stadium and you have ryegrass or bluegrass or Bermudagrass, if you got Bermudagrass, you're mowing it at 1/2 an inch. What if you mowed it at 3/4 of an inch or 7/8 of an inch? Get it up that much higher, you're going to have that much more leaf area to absorb sunlight. Kind of a rule of thumb is apply about half of the nitrogen fertilization that you would if that plant's in full sun growing. You put too much nitrogen down, it's going to cause that rapid shoot growth, and it's actually going to weaken the turf. So you got to limit your nitrogen applications. Apply a little bit of a slow release, different times of the year, make it available. But at least 25-50% of your fertilizer should be in a slow release form for that plant. And just, again, half the rate you would in full sun. Again, you can look at their studies looking at nutrients. No nitrogen versus normal nitrogen under heavy shade on bent grass. You can see it looks a lot worse on the right, just because it's caused that shoot growth with that nitrogen response. PGRs. This was a neat study with fertilization done at University of Wisconsin, looking at Kentucky bluegrass, Supina bluegrass, and creeping bent grass and Supina bluegrass. And what they found was that foliar versus granular, same rate of nitrogen, but they did a foliar versus a granular application. what they found was on Kentucky bluegrass, they had a better response to granular applications than they did foliar. The foliar had lower quality, and maybe it caused it to grow too rapidly when it was applied to the leaf. Bent grass is the opposite. Fortunately, we don't play sports on bent grass except for golf or lawn bowling, maybe. Croquet, I mean. But the foliar response was, and that's what most golf course superintendents are doing, these light foliar applications to their greens. Didn't matter for supina bluegrass if you did a foliar or granular. It had the highest quality, and it responded well. But again, it's a really shade-tolerant grass. Here's, you can see the granular versus the foliar apps. There's a 1/4 pound of N per 1,000 square feet every 14 days on Kentucky bluegrass versus the foliar app.
Has anyone done anything like that on warm season grasses yet?
No, I was just going to say, this hasn't been done on warm season grasses yet. So it'd be interesting to see how Bermudagrass or even zoysia grasses respond to foliar versus granular apps. Unfortunately, no. But, different responses. Bluegrass has better uptake through the leaves, or bent grass had better uptake through the leaves. The bluegrass had twice the root mass with the granular applications, and it didn't, supina bluegrass was the superior one. Again, watering, there's that debate, light frequent, deep infrequent. Remember, roots don't have brains. They're not going to chase a water gradient because they think it's deeper. But, water, when it comes to watering, the rule of thumb is think of photosynthesis. Sun plus CO2 plus water yields energy. So never make water limiting, but don't overwater. That's what I say. So and you can make a gradient, go down, you want some water, let it chase it, but know that turf in shade is going to lose water a lot slower than turf in full sun. So full sun, if you're having to water your turf 3 times a week because it's sunny, low humidity, windy, if it's in shade, it might be 80% shade, you only have to water maybe once a week because it's going to be, 60% less water is going to be lost because it just doesn't have that sun to evaporate it and cause evapotranspiration to occur. Use a soil moisture probe. No, it's just a simple tool. Don't care what brand it is or whatever. Know the moisture of your root zone and don't overwater. And don't make water limiting. So consider the environment, cool canopy temperatures when you look at water, restrict air circulation when you're in shade, reduce photosynthesis, metabolism. You don't have to worry about tree root competition, but these are things of why you got to reduce your irrigation under shade. Diseases, even if sunlight is sufficient, growth in shaded turf may still die or be weakened by one or several diseases. Bluegrasses are very susceptible to powdery mildew when it gets low light, cooler temperatures. Powdery mildew isn't typically a disease that kills bluegrass, but when you're in shade and you compound it with traffic and reduce growth, then that can reduce and you start to have turf death that can occur. But it also moderates the extremes, so that turfgrass environment or that disease environment, you look at the disease triangle, the susceptible host, you got a more susceptible host of turf under stress and shade, the pathogen, which is always there, now your environment, it's always humid, it's a good microenvironment for that fungus to start growing and affecting the plant. Things like pink snow mold, very, very common. So shade reduces the length of time that the leaves stay wet. Again, increasing the susceptibility to diseases. So here's some pink snow mold, microdochium patch on Kentucky bluegrass. Other diseases, leaf spot, rust, rhizoctonia are very common under low light conditions. Powdery mildew on Kentucky bluegrass, right next to it on the supina bluegrass. More shade-tolerant grass, less susceptible of a host for disease to get affected, and we don't see the powdery mildew on it because it's healthier and growing actively. Bluegrass wasn't too much shade. Again, that bounty layer staying wet on the leaf. circulating air. I got to be involved years ago when I was a graduate student at Michigan State. And when I said don't trust architects, I learned that from my old advisor, Trey Rogers, because he got to work with an architect, and that's when it was good. Then you can start to trust them if they come to you and ask for help. That's the best thing that can happen. So in the 90s, late 90s, we're going to build a new stadium in La Plata, Argentina. And the architect said, what do we need to do? And so Trey said, the best thing you can do, because at the time it was before SGL lights were out there, so they were going to have lights, and they wanted to have a portable field to move in and out of the stadium. So they're going to build it in modules. That was the plan. So he said, you need 4 entrances to the stadium, not just one entrance. It would take forever to move the field in and out. So on the 2 ends and on the sides, they have big entrances, tunnel entrances, where you could bring in the portable fields and start and put it in, and then go in and take it out as you needed it. And they also go, if you go to that stadium today, all around the wall, at about 2 meters up, or not 2 meters, about 1.5 meters up, every meter, there's a little tube, and it shoots air. And you can circulate air across that whole field to change some of that environment to make a more favorable condition for growth. Golf courses put fans on their greens. Anything you can do to circulate air. Now you can buy the big turbine fans or fans to go cool breeze or whatever the fans are to blow across your surface. That helps under low light conditions. Reduces that disease pressure. Plant growth regulators, PGRs. A lot of research has shown that PGRs improve the shade tolerance of turf grasses. Whether it's Supina bluegrass, that's already a really good shade tolerant grass, or Bermudagrass, which is the worst, it does better if you can use a PGR on it, especially the type 2 PGRs like Primo that are late GA inhibiting growth regulators. They slow that elongation of the leaf, so that's less energy that it's going to elongate, and it absorbs the photosynthesis. Here's diamond zoysia under 90% shade, and here it is under 60% shade up here. And they put these shade structures on. You can see with and without the PGR, you can't really see much of a difference when it's 60% shade, but you get heavy 90% shade. On the left-hand side is where they put Trinexpec ethyl, Primo. Right is where they didn't. You can see simply using a plant growth regulator how much it improved the shade. This is work done at A&M, if you guys didn't know. A couple A&M students up here. So, Zeon zoysia grass in the National Stadium in Singapore, they went from ryegrass to Bermudagrass. Now they're using, and then a japonica type. Now they're using a Matrella type Zeon zoysia grass in their stadium. It's playing great. Biggest concern was, will it hold up to rugby? It's a pretty rough sport, right? So rugby 7s and even 15s, so the scrums pushing on it, because what they've gone to with this stadium to manage their shade, all from budget and economics, is they have nurseries and they'll put this in, and it's never in for more than 3 weeks. Then they roll it up, take it out, put it in their nursery, and they got another one, they bring it in and put it in. So, sounds like a lot, but it's a lot cheaper than they trying to keep grass in the stadium. It was designed by a French architect. Hopefully there's no French architects in here. Where that southeast corner, the sun never, they're 14 kilometers north of the equator. The sun never hits the turf on that southeast corner because the roof covers it so much. Last thing they thought about was the grass. You know what they have in the stands? Because it's hot and humid in Singapore? They got little vents that blow air on every spectator, so it's nice and comfortable for them. Architect thought about that. Didn't care about the pitch, right? Didn't think about the pitch. But PGRs, how do they work? This is a study we did. Don't mind this is back when the very first digital camera came out. Had the Sony, and you stuck the 3.5-inch floppy disk in it, right? Not a very high-resolution picture. But in doing this work in '98 in La Plata, Argentina, we built a little simulator dome that the stadium was going to have. And, this is Poa supina, the most shade-tolerant grass we have. under 90% light, you can still see it's kind of spindly. You add PGR, look at the increase in root mass. Look at the thickness of the leaves and the more stolons. This is a grass that grew by stolons. So you can see how these PGRs improve the quality of this turf. How do they do that? Remember when I said how compared Kentucky bluegrass versus Polycypina in terms of how they photosynthesize, and Polycypina photosynthesize at 1.5 micromoles per meter squared per second versus the 1. Well, if you take Kentucky bluegrass and you add a PGR to it, it improves its efficiency for photosynthesis. Not quite as good as Polycypina, which is 1.5, but it's at 1.4 micromoles per meter squared per second. So this is another tool. A plant growth regulator on your turf under shade is going to improve its efficiency for photosynthesis, whether it's a shade-tolerant grass. You saw it in the diamond zoysia grass. Worked on that. Works on Bermudagrass. We've tried it on Bermudagrass. We've done it on Kentucky bluegrass, Supina bluegrass, tall fescue, ryegrass. They all improve their shade tolerance under low light with a PGR. How often do you need to apply it? It doesn't matter, but what we find is in full sun, the metabolism breaks down that growth regulator, and they typically go golf courses and they're doing their greens in full sun every 2 weeks. Because everything's slower under low light conditions, the metabolism of the plant slowed down, you could go away with monthly applications of applying a plant growth regulator, and still have the same effect. So it doesn't matter if you go every 2 weeks or once a month. You're okay. What about grow lights? Limited work on them. Some of the early work was done at Michigan State by John Steyer, who was working on his PhD for Trey Rogers at the time. Then he went on to be the turf professor at Wisconsin for 14 years. And now he's the associate dean of the college at University of Tennessee. So he's went from my boss during the World Cup days, told me to go to grad school. He moved on to Wisconsin. Now he's back at Tennessee as my boss again, which is good. But we set up a study this year looking at some of the light structures. And the work that John Steyer had done was looking at high-pressure sodium versus metal halide lights. He found that the metal halide lights and high-pressure sodium lights all did really good for growth. The biggest difference was the metal halide lights had more blue in them, and they had a more short, sturdy growth in the indoor conditions. I don't know why people don't use more metal halide. I don't know. Mark, I don't know. You know why? Or probably it's more expensive, not available, high-pressure sodium. But so we looked at a study where we built a shade structure, as you can see here. And I call these like little individual foam booths. So this yellow light that you see in here, that's the high-pressure sodium, no light. And then the red one here is the LED lights. And we're comparing high-pressure sodium versus LED. And then we had turf outside in full sun. So how does the full sun versus no light? And this was about 95% shade. Is that right, Taylor? In these, because this is north-facing, so the sun never hits directly onto this, but we got a heavy shade cloth around it. Then each one has a shade cloth around it. So we really reduced the lighting that hit the turf. This is brand new. We just started this last fall. So early in the study to get a lot of the results, but we started with Bermudagrass, and then we also did bluegrass. We just finished up the bluegrass in December, testing it. But the big thing was we grew the turf out, and then we moved it in modules. So those ITM modules, if you remember those back in the 90s that were around, we used those. So high-pressure sodium, LED, no light, which is about 95% shade, full sun. And then the two different turfs we used were Bermudagrass and Kentucky bluegrass. And what we did is we moved them in, and we looked at them over a 7-week period and to see how changes occurred over 7 weeks. So some of the early data, if you look at the percent green cover, LED light, having LED light. So this is the full sun, the one that was outside that had no shade restrictions. We had about 95. You never have 100% green turf cover because when we take digital pictures, we analyze it and there's some shadows being cast on the grass itself and it picks that up. So, basically 100% cover is 95% green turf cover. High pressure sodium was slightly lower, but only 1%, but it wasn't statistically different. For 7 weeks, the high pressure sodium lights maintained the same green color as, or percent green cover as outside. The LEDs were better than the no light, which was down to 70% after 7 weeks. They were still over 80%, but they didn't do as much. And to me, I was looking at this and I was like, that's weird, because I did some other LED work that I'm not showing in here earlier on in a controlled growth chamber environment on ryegrass. We found that the LED light really improved it. And it was looking at the different ratios, though, of blue light. We had more blue light probably on the LEDs we did in the growth chamber than we did on these outdoor ones. So again, you can pick the individual diodes or wavelengths of light you use when it comes to LEDs. But that technology is just starting to get there. It's a lot in the horticultural industry, but we're still trying to learn and get there for definitely for the turf industry. Rooting, everything lost its rooting when it was in shade. Well, the percent cover with the high pressure sodium light wasn't different than the full sun. It still wasn't getting all the energy that it could have to have as much as the full sun, which had greater rooting. These are high pressure sodium. After the study was done, we took them out of the little phone booths. The no light control, and you can see the kind of the yellowing here of this is the LED ones. So you can see after 7-8 weeks, the quality, the percent cover dropped down a lot. Another thing we started looking at, see if my grad students start to convulse a little bit, because they had to go and pull samples and measure from each of the nodes the distance of how the nodes were and all things. So under full sun, this is the stolon growing. You got a nice branch coming off, good healthy stolons. LEDs, a little bit more elongated. No light. See how it gets that spindly elongated? The high pressure sodium, it had greener turf color than the other ones, but it also had more elongated than the LED light. So the LEDs did cause a shorter, sturdy growth, but just didn't cause enough growth. We didn't have enough intensity of it, I think, for it to grow. But they're more shorter and sturdy. But the high pressure sodium was kind of in between the full sun and the shade in terms of the elongation of the leaves, because high pressure sodium has a lot of yellow light. That's why when you see it, it's a lot of yellow light. So that has that inherent elongation effect from it. That's one of the things that you see when you use these in these stadiums. High pressure sodium lights provided the same amount. Let's go to 915. Right, okay. Not 10, or not 9. Good. So high pressure sodium lights provided the same amount of green cover as the full sun plots, but it had slightly reduced rooting as a result. And shade increased the internode lengths on all plants compared to full sun. Kentucky bluegrass, this is literally hot off the press that we've done looking at it. Looking at dark green color, the LEDs had the lowest dark green color index ratings versus the full sun, the control, and the high pressure sodium plots actually had even higher than the indoor control, but they were same as the full sun. Quality ratings, even the control had a little bit better. This was strange, so we're still interpreting this data and trying to look at it what it was, but this is a quality rating because it just looked different, the turf, and so it's a qualitative assessment or an assessment of like why is it looking that way. So again, we got to start to figure out what are the right ratios of LED lights if you're going to do this, of wavelengths, which ones you're going to use. And this is where I've just started to learn also. This is my definition of an ignoramus. I'm teaching you something I just learned, right? So we just hired a new position at the University of Tennessee, and it's a plant physiologist, and their whole job is to do controlled environments. So greenhouse production for fruits and vegetables and things like that, and they do a lot of work with kale and tomatoes, and it's all LED lights. And what I've learned is with the LED lights, what they're finding is with the more blue light, you can increase all these secondary metabolites in tomatoes. So anthocyanins and all these things that are healthy, nutritious, you can make them more nutritious. But what they're also adding is about 25-50% far red light. and adding that far red light with their LED spectrum, they're getting a better response and a better growth. So these LEDs that we had didn't have any far red in them. So maybe that's something we need to add. And we can improve the quality. So that's where we just got to get these technologies and learn. But here's the bluegrasses at the end of the study, including the outdoor ones. You can see the lighter green ones were the LED ones. So, again, this is just hot off the press. Some of the things we looked at on them were soil temperatures, high pressure sodium. That's also one of the benefits for cooler season climates. You know, again, you're in the UK. You got Stamford Bridge and Chelsea. It's cold. Get the lights over it. Adds that extra heat to help warm the grass. Lambeau Field in Green Bay. You've got the high pressure sodium lights over the field. In January for a playoff game, they've got the heating system below, and they've got the heat coming off of the lot from the top, as well as getting that benefit of the high pressure sodium light for the growth of the grass. So they get that two benefits of it. Now, when they had the high pressure sodium lights in Singapore in the National Stadium, it went from 90 degrees to 110 or 115 degrees. It gets it really hot. It's constantly really hot. So they don't really need that extra heat from it. So that would be one where you'd want fans to blow it away or things like that. Also, one of the reasons why they just went into a lay-and-play type system that they're using on a regular basis. So a summary on the bluegrass under this light, dark green color for the high-pressure sodium was the same as the full sun plots. LEDs had a lower quality than all the other treatments. This was, again, that was what was surprising to me from stuff I'd done in growth chambers before. But, again, is it the ratios of the blue and the red and not having far red light in it? High pressure sodium increased the soil temperatures about 4 degrees Celsius from the control. Again, going into the fall when the days are getting shorter and the temperatures are getting colder, you can also get that secondary benefit of a system like that to sustain optimal growth. And then the high-pressure sodium lights had the lowest soil water content. Again, the heat probably caused evapotranspiration more, so you got to watch these and make sure you water them separately in these plots that we had. That's a good lesson if you have a stadium too, and you've got only high-pressure sodium on your goal mouths or different areas of your fields on your south end, and you're creating higher evapotranspiration rates, and you start putting on your water, you might be overwatering other areas. So you might want to get into hand watering, go and probe your field with those soil moisture probes and know which areas are deficient in water and go back and hand water those ones. So a little summary of managing turf and shade. Limit traffic and monitor diseases closely. Apply PGRs. These are off patent now. Oops. So it's only $20 per acre, maybe, to apply. So it's not that expensive for a plant growth regulator today. Use maximum mowing height that you can get away with. Limit your nitrogen fertilization. Again, with the water, we talked about the water. Don't overwater, but make sure water's not limiting. Remove obstacles to air movement that could be blocking it, or try to get some fans, circulate air. Obviously, this would be more of a golf or home lawn situation if trees are calling it, pruning it. But, be flexible. A lot of the times they'll put the synthetic turf along the sidelines just where there's heavy traffic. And then in the middle where you're playing is where you have the grass. It's just too hard to grow grass along those sidelines where cameramen and people are moving up and down. Again, so repeat some of this, but the plant growth regulators also help you reduce the number of times you mow. So not only do they improve the photosynthetic efficiency of that plant, but if you can cut your mowing down by 10% or 20%, when you mow that plant, you create a wound, and it takes the carbohydrates that it's producing from photosynthesis to heal that wound. So if you can reduce the number of times you have to mow, that's that much less energy that can to heal that wound that it could use for root growth, a new stolon, or a new shoot to come up with that plant. Then the big thing is communicate. Communicate with your bean counters, your administrators, whoever it is, why you need to have these tools, these resources, from grow lights to PGRs, in your arsenal to grow grass under these low light conditions. Taking control of speed. How much shade do you have? Some of the best remedies they can do in golf is chainsaws, pruning, but the best pruning is bicipital pruning right at the base, right? Trees can be woody weeds. Bicipital pruning. And, got this, and if you look at a USGA green section record from the 90s, Tim Kennelly, golf course superintendent, at the Annapolis, at the Naval Academy, had I think it was a 5-star general, or a big general that played golf and loved trees. He must have been from Germany or Oregon, right? Loved trees, and he said, you can't get rid of these trees unless there's an act of God, right? So out there playing, and the general's going and looking, and they're grinding a stump on the tree that had gone down. The general's asking, what happened? Thunder and lightning. Storm, thunder, lightning, took out the tree. We're chopping it up. Wow, that sucks. That's a great tree. Caused a lot of shade problems on the golf course, but that happened to hit the right tree, right? Happened a couple more times. We hadn't had any storms. But Tim, he put on 2 chainsaws, he literally wrote thunder and lightning on his chainsaws, and one took him down. He didn't get fired. Why? Because he was an excellent communicator, though. And they saw the benefits of when those trees were down, how much better the conditions of the turf were that were affecting the game of golf. Trees have a place on golf courses, but the worst thing on a golf course is planting memorial trees, right? After a member that had died and they plant this tree, 50 years later it's causing all these problems. Well, we can't cut that down because his grandchildren are members and they don't want. So don't plant memorial trees. If any of you guys go to golf, have ball washers and benches. Memorial benches or ball washers are what you need. But there's devices out there that you can purchase to measure how much light you've got. And they measure these power meters. What was power again? Oh man, it was only an hour ago when I said it. Photosynthetically active radiation, right? The visible light spectrum, the light that's used for photosynthesis. So you can buy things and you can go measure, 1,600 micromoles per meter squared per second. You can measure that light intensity in your stadium. That's pretty good. That's really good sunny conditions. You can kind of map it on your field, transpose it. You got really low light on one end, high on the other, or shade problems, looking at things. Measuring these lights in the photosynthesis. There's other meters you can get and go around and just different spots and track it. See what it does. Quantum light sensors, they're not that expensive, a few $100s to get these things. Have one in full sun, one in the shade, know what the difference is. Because this is a way for you to communicate. So we had this quantum light sensor, and we had one in full sun and one in shade. And you can set it up to measure micromoles per meter squared per second every hour. You can do it every 2 minutes, every whatever period you want. We did it every hour. They also collect humidity and temperature. And we had shade versus sun. You can see on the sunniest part of the day, this is the time of year, we were only at 1,500 micromoles per meter squared per second, roughly. But in the shade, the highest we got was 308 micromoles per meter squared per second. Now, you got to take these, you add all these up, and then you multiply them by 3,600, because this is every hour, but there's 60 seconds in a minute and 60 minutes in an hour, so that's 3,600. And then you get a really big number, and you calculate it, but then you can divide it by 10 to the 6, and you get it how many moles. That converts it to moles. So here you map it out on, here's the full sun, here's the shaded area. Again, these are the numbers when you multiply them by 3,600, how big they get. 8,645,486 micromoles per meter squared per second in full sun. Divide that by 1,000,000, gives you 8.6 moles of light per day. Sorry, that was in the shaded area. So you got 8.6 moles. Again, go back to that map where you've put it on there. You've logged it in Excel. Full sun was 48 moles. Shade was 8.6 moles. You know, you divide that and you get 18% full sun. These are ways you can go and you can take control of measuring how much shade you have and then say, look, if I get some supplemental lighting or I get PGRs to add to my bill, I go with a more shade-tolerant grass. This is how I can improve the conditions of our turf in our stadium. Another app. This is one of my favorite apps. I've killed many, many trees on golf courses with this. I think I'm over 200 trees now. But it's Sunseeker. And this is an app that was originally developed by interior decorators, for interior decorators to go in and architects, when they're building a house and they get the feng shui, we need a window here, and this is what we want the house and all that. Well, we found it in the turf world, and we use it to kill trees. Because we go around on golf courses, you get this app, and it tracks where the sun is. So I'm standing on the south end of Neyland Stadium in Knoxville. You can see from the first picture I had, they got a new Jumbotron, a bigger one, caused more shade, right? This was Monday, May 5th, 2014. I'm standing there, and it was 12:55 p.m., so just about 1 p.m. where the sun's at the highest point in the sky. And so you could take a picture. This is pointing to where the sun is. This is where the sun is at 9 a.m. on December 21st, 10 a.m. on December 21st. It's not hitting that south end. Fortunately, the football season's done at Neyland Stadium. But if this was Nissan Stadium where the Titans are still playing, right? Not at home, though. They're on the road, the last couple. But still, if they were playing at home, it'd be similar, same latitude in Nashville as Knoxville. You get shadows casting on that field, trying to grow the Bermudagrass or overseeded ryegrass into it. You track 10 a.m. where the sun is. 11 a.m. on December 21st, it's still in shade. And you can see they're going up. There's where the sun is. It blocks it out. But you can just keep taking pictures, and you can see where the sun, and you can track that pattern of the sun and where it's going onto your field. Coming down, all of a sudden, here's those big jumbo sky boxes blocking the sun in the afternoon. May is a long day. It's getting close to that June, where it's the longest days of the year, June 21st, right? So here's that red line is June, where the sun would be on June at those times, so at the highest point. But they're not playing football in June, Neyland Stadium. They're playing in September, October, November. So that sun might be down here at that time of day in October, late October. Again, going down, so you can see blocking it. Lighting systems can be used. So you can see whether this is Amsterdam Arena now, and I showed that picture back when in the 90s when they had to resod it all the time and how low quality the turf was. Now they don't resod. They just have grow lights instead. Do they work? This is Lambeau Field. You can see where they're using them on the south end. They didn't paint this field differently. This is just where they've moved the lights back and forth and the grass is growing out of it. It still hasn't grown over on this end because, one, the temperature and the lights aren't causing as much growth, so you can still see the logos and the paint still on that end. I love this picture because it's a good testament of how these lights can help, sustain growth when growth wouldn't normally be happening. It's still green, but it's just slow because it's cold and low light. So, take-home points. You understand light. You understand photosynthesis and the importance of that for the plants to grow. Types of shade, we did go into different types, but you got stadium shade, dense shade, the effects of shade on turf, what it causes, problems that arise from it, what you can do, management, just keeping simple with the primary cultural practices of mowing, fertilization, irrigation, cultivation, pest management. Some research that showed how using PGRs improves it, how the lights improve shade, picking the right species, and varieties. Varieties are different. I didn't go into much detail on varieties. but taking control. The key is, that communication that you do to justify why you're doing what you're doing in your stadiums and on your fields is key. With that, we got about 4 or 5 minutes for questions, and thank you guys for staying awake. And any questions? No? I covered everything, didn't I? Trey?
John, do you see any instances, we see this a lot in golf now, where we over-regulate the turf in shade?
Where they over-regulate with PGRs? Yeah, so it's limited data on that, but I think it goes back to that one slide I showed that was done at Wisconsin, again by Steyer, who's done a lot of work, was showing bi-monthly versus monthly applications of PGRs. You don't need to go every 2 weeks. You can go monthly because the metabolism slowed down on that plant under the low light conditions that PGR is still going to have an effect.
So using growing degree days,
Mm-hmm.
and being able to track that.
Right. Bill Keyser has done a great job with doing the growing degree days and estimating when that, or calculating when that PGR is going to wear off and come back with your supplemental application. Definitely. That's a great point. And your growing degree days in shade, you're going to want to monitor the temperature in there because it's going to be different than it would be on full sun. Well, thank you, everybody. And if you want a copy of this, actually, you can send me an email, and I can send you a PDF version of it so you have it, because this is a resource for everyone to hopefully use. So, Sorochan@utk.edu. And @Sorochan is my Twitter if you want to tweet how awesome this was, right? Or not, but thank you, guys.
Thank you, Dr. Sorochan.